Yesterday we defined a satellite as anything that orbits around something else. Now, the kind of satellite that we want to deal with in physics 20, is the kind of satellite that exists in space. Maybe it's a natural satellite like the moon revolving around the Earth, or the Earth revolving around the sun. Maybe it's an artificial satellite like the International Space Station going around the Earth, or some other kind of communication satellite going around the Earth. But we're talking about things that are revolving around something else in space. Now, if that happens, if it revolves around something else in space, then it's going to experience a centripetal force that's always going to be caused by the same force. And that force that causes the centripetal force will always be gravity. Now, centripetal force, as you know, is mv squared over r. Gravitational force is m times g. Why yesterday did we not put in that equation? That would be a lot simpler if we just said mv squared over r equals m times g. Why did we not say mg yesterday? Is that a valid equation for the force of gravity? Absolutely it is. So why did we not put that in when we set these two forces equal to each other? Why, rather, did we say gm1, m2 over r squared? Yep. Okay. We want to find the force of gravity of something that's orbiting, sure. So what?
We don't know what it is.
Good. We don't know what little g is. Okay. M times g is a perfectly valid equation everywhere in the universe. The problem with it is we don't often know what g is. Now, you could, now that you know how to find gravitational field strength, g is equal to big G m over r squared, you could actually find it and then set that equal to this. But look at what would happen if you did. Okay, if we said g is equal to gm over r squared, okay, look at what would happen. We would say m times gm over r squared. This would be mass 1. This would be mass 2. We'd end up with the same thing. So it would kind of defeat the purpose. We might as well just say right off the top, Fc is equal to Fg, mv squared over r is equal to gm1 m2 over r squared. Now, we get an r that cancels, because there's an r over here and an r squared over here. We get an m that cancels as well. What m was it that canceled? The mass of the producer or the mass of the experiencer? Which one canceled there? Which one is the one that we use? Which mass do we use in the mv squared over r equation, Fraser? Yeah. The object doing the orbiting, the object revolving around, is the m that we have over here. That's the one that cancels out. So we're left with the mass of the producer. The equation becomes v squared is equal to g times the mass of the producer over r. Usually we rearrange that to solve for v. Okay, it could be some other variable as well. Now, we had a couple questions for homework last night on this. Page 279. Any issues with either of those questions on page 279? 2? Number 1, okay. Number 1, you're trying to find the speed of the International Space Station, 7.69 times 10 to the 3 meters per second. That's somewhere in the range of 30,000 kilometers per hour. You're going at, what, about Mach 30? The International Space Station is going at about Mach 30 as it orbits around the Earth. Okay, man, there's a ride. There's an amusement park ride, eh? You're going Mach 30, and you're free-falling, constantly free-falling for weeks or months at a time. That's the ultimate amusement park ride. This one's a little bit different. This one has a much bigger altitude than the International Space Station does. This is one that we want to be further away from the Earth because we don't want the images that it takes to be obscured by the Earth's atmosphere. So we put it way above the Earth's atmosphere. The Chandra X-ray satellite takes X-ray pictures of high-energy objects in the universe. It's orbiting around the Earth at an altitude of 114,593 kilometers, which we don't really want kilometers, right? We want meters. We want to find the orbital period. What do we got here? We want to find T. Okay, that's what we want to find. Tell me what R is. 114,593. Well, let's make it in meters. So it's 114,593,000. Is that right? We're still not right, is it? What do we got to do now? Josh, what are we going to do now? Yeah. We want the distance from this satellite to the center of the Earth, which is going to be 6.37, I believe it is. 6.38. times 10 to the 6 meters. We add those two numbers together. What do we end up getting for r there when we add them together? I end up getting 1.20973 times 10 to the 8. 1.20973 times 10 to the 8 meters. I want to find the orbital period. Any ideas here? Yep. Frequency? Yep. It's the inverse of the frequency, but we don't know what the frequency is either, so. No. No. Listen, if you don't know what to do with this, that's okay. Okay, try something. Don't be afraid of trying something. Okay, that's the thing that I really like to get across to people in Physics 30 is when it gets really tough. Okay, don't be afraid to try things. Try something that's valid. Okay, this is a satellite problem, right? We don't know where we're going with this exactly. We don't know how to solve this exactly, but we know it's a satellite problem, and we know that when we have a satellite problem, every single time we know this is applicable. We know this is valid. Okay, whether it works for us or not, whether it accomplishes anything or not, we're not sure, because every once in a while when we try something that we almost always do for a certain type of problem, it doesn't help us. But it's not wrong. Worst case scenario is I end up solving for something that I don't need, something that's irrelevant, or worst case scenario is I end up having 2 or 3 unknowns and I can't find something. That's okay. Try it anyways. Okay, we know this is valid. We've done this for all our satellite problems. Give it a shot if you're not sure what to do. FC equals FG. Let's say MV squared over R is equal to G M1 M2 over R squared, as it always is. Let's get rid of one of the R's. Let's get rid of one of the M's. And we're left with V squared is equal to G times the mass of the producer over R. Do we know what big G is here? Yeah, we do. Do we know what M is? Mass of what, Fraser? You told me a few minutes ago. The mass of the mass of the experiencer canceled, right? That's what you told me a few minutes ago. This is the mass of the producer that's left. Okay, and R is the distance from the center of the producer, which we have here. Do we have the mass of the producer here? What's the producer? The Earth. So we have its mass. We can find speed. Is it helpful to me? Don't know yet, but at least I can find it. It's something. It's more than I had before. So let's get it. Okay, let's say V is equal to the square root of 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.97 times 10 to the 24, divided by R, which we found just a minute ago, to be 1.20973 times 10 to the 8 meters. Let's get that speed now. We get the speed of this satellite to be 1,814.286 meters per second. Anybody else get that? Okay, thank you. 1,814.286 meters per second. It's not what we're looking for. Is it helpful to me? No, it's not what I'm looking for, but I think, Lane, that it's helpful to me, right? Lane, what do you want to do at this point now that you have speed? How? Good. Remember, the very first equation that we learned in this unit, V is equal to 2 pi R over T, all of a sudden rears its head again. Let's rearrange it. T is equal to 2 pi R over V. 2 times pi times R, again, is 1.20973 times 10 to the 8. Divide that by the speed of 1,814.286 meters per second. And when we do the math on that one, I think we're going to end up with 4.19 times 10 to the 5 meters, 10 to the 5 seconds, I should say. Yep. Yep. Good. Are these satellite problems all that difficult? No, I don't think so. Okay, can you do that on a test tomorrow? Okay, this would be one of the harder ones that you could see. The last example that I gave you with that geosynchronous satellite, did anybody get it, by the way? Yes? Okay, good. You're not going to see something that's quite that difficult on tomorrow's test. The mathematics of that is ugly. Okay, even when we have the equation, cube root, whatever, you're not going to see something like that on a test. I can promise you that in physics 20 or in physics 30, you're not going to ever have to cube root something. Okay? Even though, you've done that in math class, we're still not going to have to do that here. All right? Let's spend a few minutes right now giving you a quick, brief outline of what's going to be on the test. We're not going to spend a great deal of time going over each of the individual things because I've actually got to leave in about 10 minutes. You're going to work on some questions involving all this stuff for the rest of class after I've given you this outline here. Circular motion and gravitation. What do we start out with? What is uniform circular motion? Okay, what is it? Okay, those little things that go along with uniform circular motion like frequency, period, speed. Then we talked about centripetal acceleration and force. Remember, centripetal acceleration, A is equal to V squared over R. Centripetal force, F is equal to mv squared over R. Remember that centripetal force and acceleration always point toward the center of the circle. And remember that centripetal force always has to be caused by something else. So just like in the satellite problems, sometimes we're going to set Fc equal to some other force. Fc equal to Fg, Fc equal to Ff. Okay, sometimes it'll just be mv squared over R. Sometimes it'll be mv squared over R equals something else. Then we talked about centrifugal force. Why did I put centrifugal force in quotation marks there? It's not really a force, right? It's that force that pushes you out to the outside of the circle when you're going around a turn. But in the end, it's not really a force. It's a pseudo-force. Anytime we accelerate one way, we perceive a force in the opposite way. When I'm sitting in my car and I accelerate forward, I feel like I'm being pushed back against my car seat. When I'm accelerating toward the center of a circle, I feel like I'm being pushed out toward the outside of a circle. Centrifugal force. And we did vertical circular motion, VCM, vertical circular motion. Okay, sometimes we might want to define vertical circular motion, the normal force, or the force of the track pushing. Sometimes you might want to define the minimum speed. Okay, the minimum speed, remember, you're analyzing the top of the loop, and you set the normal force, in that case, equal to 0 and solve for the speed. Those are pretty common questions. We also talked about models of the universe. Started off with Aristotle in the 5th century BC. Then we went to Copernicus, 16th century. We talked about Tycho Brahe, the P guy. Johann Kepler, the P guy's assistant, who came up with these 3 laws. We'll put as a separate category here Newton's law of universal gravitation. Now, of course, within Kepler, we have to know the 3 laws, but there's no mathematics associated with these 3 laws. Newton's universal law of gravity, or of gravitation, does involve some mathematics. And of course, that involves just plain problems like F is equal to G m1 m2 over r squared. But it also involves things like, here's an object, here's an object, here's an object, each with a mass, object 1, object 2, object 3. What's the net force on object 1 due to object 2 and 3? So we've got the force between 2 objects, but also the force on one object due to 2 others. And I'll tell you right now, as I have the test in my left hand, there's one of these on your test. We have 3 objects, and you need to find the force on one of them due to the other 2. After we did Newton's law of universal gravitation, or Newton's universal law of gravitation, we did gravitational fields. And of course, with the gravitational fields, we had producers, the producer equation, and the experiencer equation. G is equal to G m over r squared. Know what a field is. Know that it's essentially the same thing as the acceleration due to gravity. Know what the difference between a force and a field is. A field requires just a producer. A force requires both the producer and an experiencer. And then know how to solve for the gravitational field. Know the difference between force and field again when you're calculating it. If you're given a question with both masses and you're solving for the force, great. Gm1, m2 over r squared. If you're given a problem involving both forces and you're solving for the field, then don't use both of the masses. Use one of the masses, either the producer or the experiencer, depending on which one's more convenient for you. Finally, what do we have? Satellites. Know what a satellite is. Spelling that wrong again, I think. Know what a satellite is and know how to analyze it. Basically, with a satellite, what do? FC equals FG. And that's going to be the case every time. Every once in a while, we throw in V is equal to 2 pi r over t or something like that. But in the end, that's the basic analysis that we always do. Done. That was a quick outline. There's not a lot to know for this unit, so it's a good opportunity to do really, really well on this test. Question number 1. There are 10 multiple choice questions, and there are 6 written questions. I'm not going to tell you anything about the multiple choice other than, that could be probably where you would expect to see something about Copernicus or Johann Kepler and Kepler's 3 laws or something like that, right? Some of those qualitative type stuff in that multiple choice. As far as the written questions, question number 1 is a centripetal force problem. Okay, it's an mv squared over r type problem. It might be a little bit more than just F is equal to mv squared over r, but that's the basic thing. Question number 2 is a gravitational field question. Not telling you whether it's a producer or experiencer. Question 3 is a vertical circular motion question. Okay, we might have to solve for a force of a track at the bottom or a force of tension, or might have to solve for a minimum force, minimum speed, or something like that. But in the end, it's a vertical circular motion question. Question 4 is a satellite problem. Be careful when you're solving those satellite problems, right? We encountered some where you were given the distance from the center of the planet to the satellite. We were given some where we were given the distance from the surface of the planet to the satellite. Which one do you really want there? From the center. So if you're given the distance from the center to the satellite, that's the one you want. If you're given the distance from the surface to the satellite, what do you got to do? You got to add the radius to it. Now, on the other hand, if you're solving for the distance that r, and then solve for r, great. If you're solving for the distance above the surface, then make sure you get r, and then you're going to do what with that? If you're solving for r, okay, if you want this distance right here, then you're going to get this distance, and then you're going to subtract the radius of the planet from that. So you got a satellite question in number 4. Maybe you're solving for r. Maybe you've got r. I'm not going to tell you that much. Question 5, I already told you what question number 5 is. It's one of these ones right here. You got gravity with 3 objects. And then number 6, it's a kind of a circular motion thing. I'm not going to tell you exactly what that one is. It's not crazy hard, but I just want you to think a little bit about that one. Any surprises to this test? I mean, really? Well, I told you there was 6, though, so it shouldn't be too much of a surprise that there was no 7th question. Really, I don't think there should be any surprises, right? What did I tell you was on the test? Well, I told you that there was a problem like this on the test. Well, like this, right? Those 2 things combined. I told you there was a vertical circular motion question on the test. I told you there was one of these gravity questions on the test. I told you there was a satellite question on the test. I told you there was a gravitational field question on the test. What's not on the test? Well, there is one more question that I kind of didn't really tell you much about. Okay. What's not on the test? Universe models, centrifugal force. Hey, maybe that is on the test. Okay, it's just not part of the written response, right? Just part of the multiple choice. There's a very good chance that those 2 things are going to be on the test as well as part of our multiple choice. Okay, so no surprises. I don't think I should be giving anything away here when I tell you what the 6 questions are on this test. Okay, maybe it helps you focus a little bit. That's great if it does. Take advantage of that if it does, okay? Okay. Use this as a little checklist. You know what the questions are, at least what the topics of the questions are. Use it as a little checklist. Do you understand this topic completely? Check it off. Do you understand that one completely? Check it off. If you don't, keep working on it. I'm going to give you a stack of questions that you can work on under your textbook. You're going to work on those for the next 45 minutes or so in class as I go off to church here in a few minutes. We're going to ask you to work on those questions. Work on them tonight too if you have trouble. I'm not going to suggest necessarily that you work on them in order. Just work on them. Work on the ones that you need to work on. Okay, if you need extra help with this topic, with vertical circular motion, Josh, then work on more questions with vertical circular motion. Okay, if you need more questions on satellites, then find some satellite questions and go over those. You're not going to get all of these finished during this class. That's okay. Just work on what you need to work on. Skip around and do what you need to do. And listen, if you think you're good for tomorrow's test, well, you know what? Just keep working just in case you're not good for tomorrow's test. Travis? Yeah. All right. That's it.